There are many definitions of real-time, but all agree that it means a deterministic reaction to some event, no matter when the event occurs. In terms of an operating system, this means that the OS never disables interrupts for longer than a given, well-defined time. Also, any non-blocking OS function will always complete within a guaranteed time. In some cases, real-timeliness may cost performance, as in the case of memory allocation and freeing. A very fast algorithm may not provide the required determinism and can therefore not be used. An application has RT requirements when it should always react to some event within a bounded time. Next to using a proper RTOS, this also requires that the application behaves in a deterministic way. In other words, to get real-time behavior in an application, an RTOS is required, but is not enough by itself. Although real-time by itself does not say anything about speed, usually there is some performance requirement as well. It is, however, important to remember the difference between the two factors. When a system provides the required real-time functionality but is not fast enough, usually a faster CPU solves the problem. When real-timeliness is lacking, this cannot be corrected by using a faster CPU. Real-time behavior is like a dictatorship. Rather than give all threads a chance to run, we always let some preferred threads have their share. If there is not enough time left, some threads may not get a chance to run at all. In a typical RT environment, this may not be seen as bad. Contrary to this is the time-sharing system, where the OS makes sure that all threads run eventually. In time-sharing OS, priorities provided by the programmer are no more than hints. There are two reasons why Windows by itself may not be the proper operating system for a real-time application. It does not provide determinism. Some documents classify Windows as a soft real-time system, but the fact is that Windows does not offer guaranteed interrupt latency. The Windows kernel has to be open for installing custom device drivers. Since the kernel environment has no memory protection, it opens the system for crashes, the infamous blue screens. In a real-time application, this is not acceptable. We have to distinguish between the application and the OS. An RTOS is a tool that must provide absolute real-time behavior, or else it cannot be used to build real-time applications. An RTOS by itself is not enough to build a real-time system, but it allows the use of deterministic functions to produce an appropriate response time. An RT application is built on top of an RTOS but may or may not show real-time behavior. There are good cases for using an RTOS, even though the application does not require real-timeliness. For example, when building an embedded application, we may justifiably decide to choose an RTOS to only gain configurability and reliability. What does multi-threading mean? It does not mean that the CPU executes more than one thread at a time. Instead, we use this term when the operating system has a list of threads that could eventually run. Some of these can be suspended for a while because they need data that is not available yet, user input, data from another thread. Others will be ready for execution, but are not considered important enough yet. And then there is one thread that is actually executing. When the OS switches transparently from one thread to another and does it fast enough, we perceive this as if more than one thread is running at the same time. So why do we claim that multi-threading makes programming easier? Take this example system. Action 1 has to be performed every 10 milliseconds. Action 2 must be done every 35 milliseconds. Action 3 is required when input signal X is high. This could be programmed by a 1 millisecond cycle. Every cycle we check the input signal, and if high, we do action 3, every 10th cycle we do action 1, every 35th cycle we do action 2. Typically we waste a lot of time just checking. With multi-threading, this is reduced to 3 independent threads, each with their own events. Real multiple execution occurs when we have more than one CPU. This is called multiprocessing. Depending on the OS, the programmers will see this as a single CPU that has a better performance, symmetric multiprocessing or SMP. This is the Windows method. Another method is built on multiple less independent thread execution centers, asymmetric multiprocessing or AMP. Eantime. The RTOS used in this course uses AMP. Eantime can be utilized single core or several cores. Which one of the threads should run when there is more than one in the ready state? Some OS implement a first in first out, FIFO, principle, which gives all threads an equal chance. But there are also situations where one thread must get service before another. Think of handling an incoming network message versus updating a disk file from the cache. In such a case, the programmer can assign a priority to each thread and the OS uses the priority to choose from the list of ready threads. Some OS use a high number to mark important priority. In this course we will use the Eantime convention. 0 is the highest, more important priority. The numerically bigger the number is, it is less important, lower priority. A thread is only interesting for the thread scheduler when it can do something useful with the CPU, in other words when it is in the ready state. In some OS a thread is always ready and can waste CPU time by polling for an event. Most multi-threading systems have the notion of event, something caused by hardware or software that a thread can wait for. Examples are an interrupt generated by a hardware device when it needs attention. A message produced by a thread that needs to be processed by another thread, possibly for transmitting to a device. A signal generated by a thread indicating some alarm condition. The passing of a certain time period.